Your machine learning force field is almost certainly trained with Atom, the same optimizer that trains chatbots. For interatomic potentials, the optimizer was the blind spot while everyone pushed architectures and datasets. A Harvard team plugs 3 matrix-structured optimizers, Muon, SOAP, and SOAP and Allegro, and one of them cuts the force error by 60% while needing only half the labels. The setup. A neural network fits quantum mechanical reference energies, decomposing the total energy into local atomic contributions. Forces are the negative energy gradient, Hellman-Feynman, free once you have energies. Training minimizes a weighted energy plus force error. Here is the catch. Cheap DFT forces are nearly free, but coupled cluster and diffusion, Monte Carlo force labels are prohibitively expensive. So label-efficient training, dropping to 5% or even 0% forces, matters for higher-level theory. 4 optimizers enter. Atom takes an element-wise second moment, treating every weight as a scalar. The matrix-structured ones treat each weight matrix as a matrix. Shampoo builds row and column covariance matrices, a Kronecker approximation to the full preconditioner. Muon runs Nesterov momentum, then orthogonalizes the update direction with a cheap Newton-Schultz iteration, no full singular value decomposition. SOP projects the gradient into Shampoo's eigenbasis, runs an Atom W step inside it, projects back, and SOP Muon adds Muon's orthogonalization and an RMS normalization on top. On the solid acid CDP, full energy plus force training, force error, lower is better. Atom W sits at 32.2. Muon and SOAP both reach 29.6. SOP Muon wins at 27.8, a 14% cut. The matrix structure, preconditioning the gradient by local curvature, buys real accuracy at full supervision. Now the label efficiency story, the paper's strongest claim. CDP force error as you drop the force labels. Atom W at 100% sits at 32.2 and degrades as labels leave. But SOAP Muon at 50% forces still matches Atom W at 100%, 32.5 versus 32.2. Better optimization can partially pay for reduced access to force labels. SOAP Muon holds the trajectory on the physical manifold, matching ab initio molecular dynamics, and reproduces the experimental proton diffusion activation energy of 0.42 electron volts, dead inside the. Half the expensive labels, the same accuracy. Here's the physical picture. With only 5% of forces, Atom W trajectories diverge almost immediately, flying apart into non-physical configurations, measured range. The most dramatic win is energy-only training on CDP, 0 force labels. Atom W force error, 503. SAPE Muon, 201, a 60% cut. When forces are completely absent from the loss, just preconditioning the gradient recovers most of the force accuracy that Atom W enjoyed with full supervision. 3 honest caveats. First, Muon is the partial case. On water, Muon's energy is almost twice as bad as Atom W. The orthogonalization step is the source of the degradation. Second, the 4.9 and 5.8 times wall clock speedups are figure only, with no numeric table. Third, SOAP Muon needed a learning rate 10 times lower than Atom W and extra per system tuning on water. The robust drop-in default is plain SOAP, no extra tuning, only 2 systems and 2 architectures. Beyond Atom. Matrix-structured optimizers for interatomic potentials. SOAP as a drop-in default, SOAP Muon when labels are scarce, and Muon as a caution that orthogonalizing the update can break as much as it fixes. Subscribe for the next breakdown.